Good day to you all. Welcome to the webinar about the Huygens Array Detector deconvolution option. We are happy to revisit this Huygens option, which was released last year fall with the current Huygens 1810 version. During this webinar, you're welcome to submit questions using the form at the right side of the webinar page. We will try to answer your questions within the next 24 hours. In this webinar, we will explain the Huygens Array Detector option. This option is also designed for deconvolving images from the Zeiss Airyscan microscope. Previously, we have shown that Huygens is capable to resolve 100 nanometer using the 100 nanometer rulers from Gataquant. This week, we've obtained results with nanorulers indicating that Huygens can resolve 90 nanometer spaced objects from Airyscan data. But more on this later. Let's have a look at the differences between a confocal and array detector system. In confocal laser scanning techniques, the excitation laser illuminates a specimen one point at a time. The emitted light that travels back to the detector is filtered out by a pinhole that rejects the out-of-focus light. The remaining light that reaches the detector is integrated into one single intensity value. So the confocal setup, although suitable for many applications, discards information at two stages. First, the pinhole rejects signal coming from the emission point, and second, the detector discards information about the spatial distribution of the emission light. With array detectors on the other hand, you can leave out the pinhole and collect not only more signal, but also information about the spatial distribution of the emitted light. So the distribution of the emitted light is preserved. The Huygens Array Detector option supports any kind of array detectors, including the nanospot and the Zeiss Airyscan. Because of its popularity, we focus here mainly on the Zeiss Airyscan. The Zeiss Airyscan can work in 4 different modes, namely standard confocal, virtual pinhole, super resolution and fast mode. Huygens supports all these 4 array scan acquisition modes. We will also support the new Zeiss Airyscan 2. First, images acquired in confocal mode can be deconvolved in Huygens by using the confocal option. In this case, the size of the physical pinhole is used for deconvolution. Second, images acquired in virtual pinhole mode can also be deconvolved by using the confocal option. In this case, there is no physical pinhole. Instead, you use the size of the selected virtual pinhole for deconvolution. Third, images acquired in super resolution mode can be deconvolved in Huygens with the new array detector option. And finally, images acquired in fast mode can also be deconvolved using the new array detector option. In the following slides, we're going to review the last 2 acquisition modes in combination with the new Huygens array detector option. For confocal deconvolution, I'd like to refer you to our Huygens manuals and the SVI website. I like to emphasize that Huygens can also deal with multiphoton excitation within all these 4 acquisition modes. So let me describe briefly how the different array scan acquisition modes are handled in Huygens. In order to deconvolve array scan images in Huygens, we first open the CZI file. If the CZI file contains array detector images, then Huygens will detect this and will read the pixel data from all the detectors. If the file contains multiple images from different acquisition modes, then a dialog can appear as is displayed here. Sometimes the file can also contain the process data. Notice that you only need to open the raw Array detector images since Huygens deconvolution works with unprocessed pixel data. Depending on the acquisition mode, the image will contain either 32 detectors for the super resolution mode or 16 detectors for the fast mode. This can be confirmed by selecting the new images in Huygens and checking out the image statistics. All Huygens slices and renderers support visualization of the detector images. Like with images from other microscope types, Huygens generates a PSF specific for each image. This PSF is based on the acquisition parameters, which can be read from the image file. The Huygens parameter editor gives you a complete overview and facilitates the reviewing and editing of the image parameters. So for each channel, the microscope type here is specified and can be edited as well. Here you see the detector model specified per channel. And you can edit that with this option, which designates the microscope type. The Huygens HDF5 and ICS file readers and writers support array detector images and their metadata. So how do we combine the data from the different detectors for optimal deconvolution in Huygens? So for both the Airyscan and the 32 detectors and for the fast Airyscan, the 16 detectors. We've therefore created an extra deconvolution parameter in Huygens, which we call the array detector reduction mode. I will focus here on the SuperXY mode, since this option offers a very important advantage over the other modes. Deconvolution with this Huygens SuperXY mode generates an image with more pixels in X and Y, which makes room for a super sampled image that features super resolution. The clear advantage can be clearly observed in images of 140 nanometer rulers that we have obtained from Gataquant. These images have been acquired under undersampled conditions with pixel sizes of 80 nanometer in X and Y. So 2 pixels would cover 160 nanometers, which would be too big for this 140 nanometer nanoruler. In the Confocal version of this dataset, you see the sum of all detectors. The nanorulers cannot be recognized, but with Huygens SuperXY deconvolution, we can easily resolve the 140 nanometer spacing between the fluorophores on these nanorulers. I like to emphasize that the raw images have been kindly provided by Christopher Lagerholm from the Wolfson Imaging Center from the University of Oxford. Because Huygens SuperXY mode during deconvolution allows undersampling, you can image faster, have less photobleaching and phototoxicity, the signal can increase more than 10 times, and you get super resolution data from your undersampled data. So how far can we go with resolution? Again, Confocal imaging has a hard time separating these 100 nanometer nanorulers, let alone the fluorophores that they contain. But with Huygens deconvolution in SuperXY mode, we can clearly resolve the fluorophores on these nanorulers. So these fluorophores on these nanorulers are 100 nanometers spaced. And this is a result that we showed also in our previous webinar about the array detector option. Interestingly, this week we've obtained again data from Christopher Lagerholm regarding the 90 nanometer STET nanorulers. Again, with SuperXY mode in Huygens, we can easily resolve these 90 nanometer space fluorophores. This is indicated by the line profile of a representative nanoruler. In fact, we tested all nanorulers with the Gataquant analysis tool, and you see that the distribution of the distances is gathered around 90 nanometer. So how are we able to achieve these amazing results on Zeiss Airyscan images with Huygens deconvolution? Well, of course we need to start with properly acquiring data. And then Huygens makes a difference at several levels. First, there is the use of the maximum likelihood estimation algorithms in Huygens. More on this in a second. The point spread function is accurately modeled for each specific image by taking the exact acquisition parameters into account. Very soon we will also support experimental PSFs that include aberrations of the specific imaging system that you have. So Huygens deconvolution and the PSF generator can even take care of spherical aberration correction. Then we also have the point that Huygens can process via the multi-GPU, so if you have multiple GPU cards, those are supported, and brickwise processing can be applied, which enables you to deal with very large data sets. Then there is also the possibility in Huygens to use additional restoration tools for correcting other imaging problems. The Huygens iterative MLE algorithm allows for the correction of spherical aberration, as I mentioned, by including point spread functions that are specifically designed for each depth within the sample. This specific depth correction ensures that similar type of objects are properly restored to similar structures, irrespective of their position within a 3D sample. And you see that here with a confocal dataset where a paramecium was imaged just above the cover slip. The objects are somewhat elongated deeper in the sample. They're more elongated, and after automatic correction of spherical aberration and deconvolution, the objects look more alike. Several deconvolution algorithms exist with the intent to improve image quality. Yet most of them cannot control for noise in a proper manner or are prone to clipping artifacts, because they do not take care of the a priori knowledge that you can have that negative values are not represented in an image. Thus these values need somehow to be compensated. Also, the limited noise model of linear filtering provides a high risk of noise enhancement and ringing artifacts in deconvolution results. Maximum likelihood estimation algorithms are iteratively constrained and regularized and can take care of these issues. In this experiment, we show that 140 nanometer Cataquant nanorulers cannot be resolved in a confocal setup, or if you sum the detectors. But if you deconvolve this dataset with a linear algorithm, so the less advanced algorithms, you can somehow resolve some structure, but if the noise model is not correct, you can create artifacts, and you see a noise amplification here in the background. So this is due to an incorrect modeling of noise. Also we see light signs of ringing, which is a potential issue with linear filtering. Due to its advanced regularization and the Huygens iterative GMLE algorithm, we can control the noise levels and at the same time resolve the nanorulers fluorophores much better. In the next experiment, we show the effect of noise amplification or background in general on colocalization analysis. So if we do colocalization analysis, we can focus on a Pearson coefficient. And the Pearson coefficient is 0 if there is no correlation between the channels. Well, these nanorulers have different colors that are quite closely spaced. So if they would completely overlap, the correlation would be +1, and if there would be no overlap whatsoever, in fact they would exclude each other, then there would be a -1 value for Pearson. In the Confocal dataset, we see a value of 0.5, 0.6. And this is for the main part also attributed to the background that you see. With the linear algorithm, the background even enhances this Pearson coefficient value. So ideally, you would have a Pearson coefficient of about 0 in the ideal world, because these nano fluorophores on the nano ruler are not co-localizing. Well, Huygens at least makes a big improvement, and it gives a value of 0.2. So we kind of separate these objects that are in different channels. And so first of all, at the ends, they're 140 nanometers spaced, these colors. That is what we can separate, but we can also identify the different channel in between these two fluorophores, which is spaced 70 nanometers from the two ends. Huygens deconvolution conserves the total signal. And that can happen because the sum of the intensities in the point spread function equals 1. So in this equation, energy is conserved. Then if we look at the linearity of signal, if you image patterns with an increase in intensity, so this sample is the Argo light sample, the 4x4 intensity sample, the patterns that increase in signal. After deconvolution, we measure the signal again, and if we plot it against the raw image intensities, then we see that the signal stays linear, and it stays linear for different laser powers even. So this result has been obtained in collaboration with the group from René Musters at the Free University here in the Netherlands. A few years ago, we obtained images from Erika Wee and Claire Brown, and these images contain beads, inspect beads from Life Technologies, and that was a calibration set with increasing intensities in the beads. If we deconvolved these beads and measured them in the object analyzer with an automated OTSU segmentation tool, then we measured the response of signal that equals the intensity series of the beats, in fact. So again, here we prove that the Huygens deconvolution algorithms preserve the linearity of signal. If you want to compare image data, so if you want to compare two images with one another in one experiment, we definitely would advise you to use templates. Templates for the microscopy parameters and templates for the deconvolution parameters, because you want to treat images similarly. You can load these templates with the image in the Huygens batch processor, and you can run the batch processor, leave, and get back the next day, and your images are deconvolved. So this really ensures that you treat your data similarly. So then an example, a nice example of the Huygens Airyscan deconvolution. Peter Hemmerich and Christian Huygens imaged nuclear bodies, and we show here an example of that. So this was an Airyscan data set from 32 detectors. We used the Huygens CMLE algorithm with an SNR of 15 setting, 40 iterations, and the reduction mode was set to all, but it was almost similar as the SuperXY mode. So in the Confocal set, we cannot really distinguish a clear hole in these nuclear bodies, and we can do that after Huygens Airyscan deconvolution. And you see that in the one-channel XY slice at the top. If we render these objects, and we in fact render 3 channels, so we have a DAPI channel and this orange channel from the top, which is depicted in yellow below, we see again the donut structures. So a clear difference after Huygens Airyscan deconvolution as compared to the Confocal data. So besides deconvolution, we also offer additional restoration tools, object stabilization, drift correction in Z and in time, chromatic aberration correction, crosstalk correction, tile stitching and vignetting correction. We offer hot pixel and cold pixel correction and also crosstalk. And coming soon, the Huygens localizer, with which we can analyze single molecule localization microscopy data, so palm storm and ground state depletion images. Then I want to present to you some quotes from users. So Glenn Nelson was quite impressed with the Huygens array detector results. We heard words about stunning results, that the resolution was improved beyond the normal limits. So we got a very good positive feedback from our users. And you can read more testimonials on our website svi.nl/testimonials. At the end, I want to thank you for your attention. Tell you that you can test Huygens yourself and the array detector option, of course. So by downloading the software and sending us the system ID code for which you are prompted. And if you send it to us, you will get a test license. So special thanks to Christopher Lagerholm for the 100 nanometer and 90 nanometer nano ruler images, Bram van den Broek en Anne Aubusson-Fleury, Pieter Hemmerich and Christian Huygen, René Musters and Jeroen Kolen, and of course Cataquant and Argolite we like to thank for the samples. I thank you again for your attention, and please send questions to us and we will hopefully address them within 24 hours. Bye bye.